Jaffe from Harvard University. You all know him. And his talk will be Remembering the Future. Thank you.
So it's really a great pleasure and honor to give this first talk. And after Wendy's talk, it's a little difficult too. I thought I would begin my talk by showing you something about Vaughan. His relations leave much to mine. His thoughts inverted time. He was our friend, and mathematics will all things mend.
Mm-hmm.
So I wanted to talk, but first I'm going to show a large number of pictures. The first one's of Vaughan. Most of them are recent, and most of them are ones that I took, so I don't think have seen them before. And then I'll show a few other pictures and then go to my talk.
You can.
Yes? Something is not working here. So there's a picture from Trinity College at Newton Meaton Institute in June of 2017 with Vaughan and Wendy. And they were having a very nice dinner. But, oh, there's with Izumi. And there's another picture in Trinity with David Evans and I think that's Susan Montgomery. And here's a picture of Vaughan at Harvard in October 2016. This was a big lecture room, and there are 8 blackboards, and Vaughan looked at this. I remember before giving the lecture, he said to me, I think I'm worried more about this lecture than any other that I've ever given. And he was thinking about these blackboards, and at the start, they were empty, and at the end, they were full. So no erasures. He had planned this perfectly, like everything Vaughan did. Here's another lecture at Harvard 2 years later, December 2018. And here, Vaughan is looking at something. Here, he's in the audience at the same meeting. And here, during a break with David Evans, talking with Jonathan Weitzman, Gene Wayne in the background. And this was a break in that meeting. You see in the front, Gester Olofsson and Carl Herman Nieb, who I saw is here. And here in the hallway at Harvard with Klaus Hepp, who was very important in theoretical physics, Tom Spencer, who most of you know, Bas Janssens. And here, I believe in Vanderbilt in March 2019, and here in October 2016 in the audience. And with Dietmar in the office that they shared at Harvard in 2016, and talking with a mathematics undergraduate at Lowell House was very inspirational for the student. Perhaps he didn't appreciate it enough. And here with Misha Lukin, who's an experimental physicist at Harvard, Vaughan wanted to see how to make quantum bits, qubits. And here we're in the experimental laboratory, where at the time there were 52 qubits. Misha's about to shut the door so people don't see how he did it. And here with Adrian Ocniano, and here in the hallway with Chengwei Liu and Li Mingge. And here in Nashville, that's Cameron Gordon. Here with Dietmar and Emily Peters in Nashville. And this was at Thanksgiving at my home, after Thanksgiving with Chengwei Liu, when Vaughn came to Boston to celebrate with relatives. And here was our dinner table. Many students there, and I'm sitting next to my daughter. And here giving a talk at Harvard. And here, another talk at Harvard, this one at CMSA. And here with Soren. This was in Bonn in 2017 at the Hausdruck Institute. And here is in Cambridge at the home of Chengwei. And Yang, Chengwei's parents, prepared this feast. And here in the restaurant with some friends of Juan and Wendy. And this one's in Nashville at a meeting. And after so many meals, you have to have a coffee. And here Vaughn is making one in my office. And here he is with Jinsum Wu, Chengwei and Dietmar. And this was another party in my home. And this was at the memorial for Dick Cattison in Philadelphia in March 2019. And here's a picture of Vaughn giving a talk on the 8th of June, 2019. This was at the Chinese Academy of Science, the Academy of Mathematics and Systems Science in Beijing. And here is the lunch after that talk with the director of the Mathematics Institute, Nanhua Shi. And here's Vaughn with his student Chengwei. That was a couple of days later in Beijing. We're about to go to lunch. And here's the lunch with Chengwei's parents. And here was the International Congress of Chinese Mathematicians in Beijing. That was the occasion. And Vaughn got an award there, which he's holding. The conference was run by Yao. Chengwei also received an award, and here are the two of them together. And this was at the dinner. And here, Pavel Exner was then president of the European Mathematical Society. He was there too. This was the announcement for the talk that Vaughn gave on the Zoom seminar July 21st, 2020. Applied Phenomenon Algebra. As far as I know, that was his last public seminar. So here are a couple of pictures from 30 years ago. Batul and Richard, who organized the meeting at, I believe it's Bacich University. And here's Batul in her office then. And Richard. And this was a stroll through the campus. And here we see some people at that meeting. Richard Nest is here, Joachim Kuntz.
Nest, Kunz, they will be talking.
Yes. But
Claude is
Claude
there on the
Itzin,
right.
unfortunately, is not with us. There's Erling, and Bob Powers, Bill Arvison.
Yeah, Erling is listening.
Yeah, George Skandalis. Sergio Dopliker. Joachim. Who's that? Claude Itzin. Ron Douglas. Phil Arvison again. And here we have a very nice dinner. Daniel Kessler on the left.
Sorin next to him.
Yes, yes. So I wanted to talk a little bit about my first trip to Turkey. And then I went to Robert College. That was 29 years before that. So Robert College became Bosage University. And this meeting was organized by Feza Gürsey. Was he at your meeting 30 years ago?
Sorry?
Did
Yeah.
Feza attend your
Yeah.
meeting 30 years ago?
No.
And this is a photo from that meeting. I found this one on the internet. It's an amazing group of people. There are 55 people in the photo. Feza Gürsey is in the front row on the right. I could identify only a fraction of the people. If anybody knows some of the people that I can't identify, I'd really appreciate your telling me about it and writing me an email.
Wigner is there, and probably Erdal İnönü is there somewhere, I will tell you.
Yes, he is in the front, in the middle. And
Yeah,
Wigner
exactly.
is in the second row, third from the left. I labeled a number of these people, the ones I recognized. But the ones I didn't label, it was very hard. Some of them have question marks because those were people who were there, but I wasn't sure that the picture matched with the person I put the label on. And it was very interesting that Feza Gürsey was able to put this group together. I don't know if he had a committee, probably had no committee. And here he had this extraordinary group of people. Many of them were fairly young. Sidney Coleman, 25 at the time, Shelley Glashow, 29, Salam was 36, Sudishan, 30, Wigner was 59, but then none of these people, this was a physics meeting, none of these people had a Nobel Prize, but afterwards 4 of them did. So I think I should show this picture to my dean and tell him you don't need a committee to put together a very interesting group of people if you have some good taste. And Faisal Gursi had excellent taste. He was a very great physicist and unfortunately isn't recognized today as much as he should be. So a year before that, I had made, so I think I was right here. Can you hear me now?
Yeah, you
It's
had
perfect.
you had left Istanbul for Montenegro. It's maybe the
Right.
next one, I don't know.
And the reason I wanted to mention the other meeting is that these are all connected. And I'm not going to give a technical result like Soren just proposed, but I'd like to show some very elementary things in their connection. And at the meeting in Herceg-Novi, I went because there were lectures by Kurt Zemancic. And Kurt Zemancic was a person, I was a student at the time. I had read some of his papers and I wanted to learn more about what he was doing. And he was just starting at the time to work on Euclidean quantum field theory. And here later, Zemancic was professor at New York University for a while in New York. I went to a seminar he organized, and here is a picture of him going to lunch with Wolfhard Zimmermann and John Lascaux, and in the back, there's Daniel Zwanziger and Jerry Brown. And here's two other pictures of Kurt Zemancic, one on the right, which was taken in his apartment in Hamburg when he was at Daisy, and on the left at a summer school in Corsica at Cargez, talking with Ken Wilson. So landmarks were the Euclidean quantum field theory, which actually had been proposed sometime before by Julian Schwinger, who talked about analytically continuing quantum mechanics to imaginary time. But it was really turned into a beautiful mathematical theory or proposed mathematical theory by Zemancic. And that was quite a few years after Schwinger originally introduced it in 1951. And then this is connected with reflection positivity, which was important in quantum field theory described by Osterwalder and Schroeder in 73, Tomita-Takasaki theory of Tomita in 1967, Takasaki's book in 70, and a beautiful paper of Iraqi and many others starting in the 1970s. And Jones' index theorem, which Soren talked about, and some recent developments connected to all these things. So what is Euclidean quantum field theory? As I say, the imaginary time field is obtained by continuing the time to I times time. And the expectations of products of imaginary time fields in increasing time order, so that if the energy is positive H, then the energy factors in this product are damping, and the omega zero is the ground state of H, which in quantum mechanics is often taken to be zero. So these expectations on the left are time-ordered expectations in the ground state or vacuum of the Hamiltonian H. And these are Euclidean because the time has been made imaginary, so you would expect Euclidean symmetry in some extent as an analytic continuation of Lorentzian symmetry. And it was Kurt Zemancic who realized that the quantum mechanical expectations on the left were actually measures of moments of a probability measure mu on the right. That is, if you extend the functions on the left, which are only defined for increasing times, t1 less than t2 up to tn, to be symmetric for all t, these are just moments of a classical probability measure. So it connects classical mathematics on the right with quantum theory on the left. And not many people at the time Zemancic introduced these ideas of a Markov field understood that this was a very deep connection and that the Markov field actually was realized on a completely different Hilbert space, L2, from the quantum mechanical Hilbert space on the left. But for time-ordered expectations, the two are the same. Sometimes the expectation on the right was written in terms of an expectation in an abelian algebra of classical fields, capital Phi, in a vector omega, which was cyclic and separating for this algebra in this representation. So the question in the mathematical physics at the time was, if you start from Zemancic's Euclidean quantum field theory, how could you get back to quantum mechanics on the left? That is, how could you do the inverse analytic continuation? One would like to know the Hilbert space inner product on the left as different from the L2 inner product on the right. And how do you obtain the unitary representation of the Poincare group that acts on the left from the Euclidean group on the right? And reflection positivity answered all three questions simultaneously. This surprise came because I'd been studying a paper of Edward Nelson, and my postdoctoral fellow and I thought this was extremely interesting, Konrad Osterwalder. And at the time I had another fellow, Robert Schroeder, who came back from vacation. Just as I went off, I told him about our interesting discussion, and I went to a conference in Chicago. And when I came back, they had discovered 4 days later reflection positivity. So this captures my title, Remembering the Future, because it takes into account the inverse of time. And it also takes the events from 1961 and 62, and later in Istanbul. It enabled me to see the future too. So what is reflection positivity? This is a question that Vaughan often asked, and he asked me to talk about it at that meeting I showed in Bonn in 2017. I don't think I did a very good job, so I'd like to try again here. If we have an anti-unitary automorphism theta that implements the time reversal, then in this classical probability theory with the expectation omega and a function of these abelian fields localized at positive time, you can consider the expectation of the time reflected A times B. And this would be very nice if it could be given as an inner product, namely if it was positive on the diagonal. And this positivity on the diagonal, the fact that this form is something that defines an inner product, is reflection positivity. So in fact, if you translate one of these functions by a positive time t, this gives a self-adjoint operator e to the minus th acting on these two vectors. And the simplest example realizing this idea comes from Sobolev space, where we could just take the delta in here, which is in this case just a Laplacian, an inverse Laplacian, and its kernel at time reflected x and x is just given by this positive function, which is the expectation of e to the minus twice the magnitude of time. Well, that's where mu is the energy. And there's this overall positive factor, 1 over twice the energy. So Osterwalder and Schroeder, in 2 papers in Communications and Mathematical Physics, proved that if you have an expectation, this classical probability theory that Euclidean invariant, reflection positive, and satisfies some analytic conditions, these are equivalent to Weitmann axioms for quantum field theory, supplemented by some analytic regularity conditions, but without assuming uniqueness of this vacuum vector omega. If correlations decay for large time, then the vacuum is unique and all the Weitmann axioms are satisfied. So this reflection positivity says that the expectation of a function f times its reflection is greater than 0 for all f, localized at positive time. And here's a picture of Osterwalder and Schroeder, and also one of Jörg Fröhlich, who did much in the development of these ideas. It's interesting that this inner product in slightly modified form works for all quantum theory examples, including quantum field theories. And so reflection positivity is something very basic and should be in every physics textbook. Now, the power of reflection positivity comes from using the reflection combined with translation in the classical probability theory, and you can do multiple reflections. So if you start with something localized in the triangle on the left and reflect it once, then you would get this pair of triangles if we reflect to the right and left. But we could move our reflection plane if the probability theory is invariant under time translation and reflect a second time to get 4. And we could repeat this over and over, each time using the Schwarz inequality, so that we could blow this small triangle up into a collection of small triangles, and eventually observe that this set of observations in these triangles could be considered a perturbation of the h in the exponent. And in fact, because of each inequality giving another square root in the Schwarz inequality, if you can estimate some perturbations of the Hamiltonian as being proportional to the volume of the perturbation, then you could get very good estimates on the triangle on the left. In fact, here I am implying that we could take not only horizontal reflections, but also vertical reflections to get this picture. That would be something from the Euclidean invariance of the theory. Now, what are immediate consequences of this estimate and the estimates on perturbations? Well, it certainly relates the Hilbert space defined by the reflection positive form and L2, but it also enabled the construction in a very elementary way of the first interacting quantum field theories and infinite dimensional analysis on this probability space, which gave analysis on the Hilbert space of quantum theory and quantum field theory. It also, using these methods and this reflection positivity bound with multiple reflections, enabled the first proof of non-uniqueness or phase transitions in quantum field theory, and later was used in statistical physics by many people to study phase transitions and establish their existence. It also was used by many people to study analytic continuation of representations to show that the Poincare group, the special relativity group, could be obtained as an analytic continuation of the Euclidean group, but also Gester Olafsson, Carl Hermann Neve, Euler, Palle Jorgensen, and others have made a tremendous theory of studying representations that are associated with reflection positivity up to the present time. So another reflection is on the 1967 Baton Rouge meeting. There, Tomita explained that if you have a Feynman algebra represented on a Hilbert space with a cyclic and separating vector, you had this wonderful modular theory. The problem was that nobody at this meeting understood this until it was written out in great detail by Takasaki in this marvelous book, leading to the big developments coming in Feynman algebra theory at the time and Kahn's classification of factors. So the transformation S was defined for the Feynman algebra A and the cyclic vector omega as giving A star omega. And its polar decomposition was the square root of the modular operator as the positive Hermitian part times an anti-unitary J. And this J, it could be shown left the cyclic vector invariant, was J, the anti-unitary was also self-adjoint, and any power, complex power of the modular operator also left the cyclic vector invariant. So it's known in modular theory and explained in Tomita's book that conjugation by S or S inverse maps the algebra to its commutant, as well as commutation by J, the anti-unitary. And we could denote S of A, that conjugation, and S of J, the conjugation by J. And J often arises in physics. In quantum field theory, for a wedge region, Bisignano and Wickman in 1975 showed that this anti-unitary J was just equal to the TCP operator theta of quantum field theory times a rotation by pi. And theta is reversal of time as an anti-unitary transformation, charge conjugation, reversing charges in physics as a unitary, and parity, that is reversing space x to minus spatial x. In this case, the modular operator delta is just the exponential of the boost for Lorentz transformation defined by the direction of the wedge. And this K is the self-adjoint generator of the one parameter family of boosts in the Lorentz group. So Buchholz and Longo have many papers analyzing the reflection as it arises in quantum field theory, and especially in conformal field theory. This reflection also comes up, as I mentioned, in statistical physics on a lattice, and it's related to physics effects called the Hawking temperature, the Hagedorn temperature, and recently connections with black holes. There are many papers by Buchholz, Fredenhagen, Dentoni, Longo, Hogg-Doppler, Roberts, and recently many other people who've studied these questions. So what is the relation between Tomita Takasaki and reflection positivity? In Tomita Takasaki, you could define a form J, which is just the expectation in the cyclic vector of B times the reflection J of A. And this is a positive form in every Tomita-Takasaki theory. I think this was first observed by Araki in a paper in 1970, which should be quoted more. And the value of the form is just the fourth root of the modular operator applied to A omega squared. So in fact, you can modify this for any positive transformation T on the Hilbert space and define a form with a T sandwiched between B and the reflection of A if T is multiplied by the square root of the modular operator. And this form is also a positive form. It's given by this formula, the inner product of A omega with B omega sandwiched with a positive transformation T hat, which is the conjugation of T by the anti-unitary J. So the previous case just corresponds to T being the inverse now of the modular operator, not the Laplacian. And the conjugation by the anti-unitary inverts the modular operator. So T hat is square root of the modular operator. Now, there's something called relative Tomita-Takasaki theory, which is also very important in physics. And that comes with a Feynman algebra, cyclic and separating two vectors, two different cyclic and separating vectors. In this case, the transformation S maps A times one cyclic vector to A star times the other cyclic vector. Again, S has a polar decomposition of the same type, where J is anti-unitary and the modular operator delta, now the relative modular operator, is positive. Again, S has conjugation of the algebra into the commutant, the same with its inverse. And J also conjugates the algebra into its commutant. But now for the relative operator, it's not necessarily true that J leaves the cyclic vector invariant. J may not be any longer self-adjoint, but it's still anti-unitary. And the modular transformation also may not leave the cyclic vector unchanged. There's a positive form for relative Tomita-Takasaki theory, which is related to the one for the ordinary Tomita-Takasaki theory, just a little bit more complicated. Now the expectation is in the square root of the modular operator times the cyclic vector omega. And B has to be conjugated by the square root of the modular operator, while A, as before, is conjugated by the anti-unitary. In fact, you could also introduce this positive operator T by putting T between the two factors, the conjugation of B and the conjugation of A. And this form is also positive. So it defines a TT inner product where this operator T hat is the conjugation of T by J. For T positive, this form is positive on the diagonal. And so it defines an inner product, and another Hilbert space. So the importance in physics was recognized in 1975 by Araki, and here's a picture that I got from the internet. I have some pictures of Araki, but I spent so much time finding pictures of Vaughan that I didn't have time to find a good picture of Araki. But what Araki proved is that the relative entropy defined between the states which in finite dimension would be associated with the cyclic vector omega, the state with density matrix rho, and the state in psi with density matrix sigma, the relative entropy given by this finite dimensional formula generalizes to just the expectation of the log of the minus the log of the modular operator in the cyclic vector psi. So if psi equals omega in the usual case, then the relative entropy vanishes. So where does Jones' planar algebras come in? Here you have a picture of a transformation T where the adjoint was given by Jones as a vertical reflection. And the product of T and S is just made by composing the diagrams. There's the other composition, which turns out to be convolution. So you have multiplication and convolution, which in ordinary theory are related by Fourier transformation. Now, Cheng-Wei Liu and I, in 2016, studied a variation of planar algebras, which we called planar power algebra, where the horizontal reflection represented this Tomita reflection J, while the vertical reflection was the usual adjoint in Vaughan-Jones theory. But horizontal and vertical reflection are related by a pi/2 rotation. So the horizontal reflection and the vertical reflection turned out to be related by a geometric Fourier transform F, which was introduced in a different way in Agnihano's planar algebras in the 1980s. So this correspondence between the Fourier transform by rotation and the adjoint gives some positivity, which is like the Hadamard positivity of positivity preserving, the Hadamard product preserves positivity, or the Schur product formula. And the Hilbert space positivity of the vertical reflection is ensured by Jones' index theorem, which Soren Popa explained in the previous talk. So the reflection positivity, namely the positivity of the J reflection in this framework, could be assured by taking a value of the index allowed by Jones' theorem and the positivity of the Fourier transform of the Hamiltonian H. We generalized this from a planar algebra to a 3D algebra in something we called QAnon language, which Cheng-Wei developed as a surface algebra in some later papers. This could be understood as a topological field theory with string defects, these strings being the strings that one recognizes as inputs and outputs in the planar algebra. And here, the Fourier transform still is a 90-degree rotation. It turned out to be very useful in interpretation in quantum information theory, where here the picture of the strings shows that you have two channels defined by four strings related to each other at right angles, which is the Fourier transform, and connected vertically. This is the controlled NOT gate as a three-dimensional picture in quantum theory. This led to Chengwei with Chenlong Zhang and Jinsum Wu, whose pictures you saw, at least Jinsum's picture you saw earlier, defining something called quantum Fourier analysis. The first thing is a quantum version of the Hausdorff-Young inequality that says the Fourier transform of a transformation in the Q norm, say the Schotten norm for subfactors, would be dominated by the P norm of the original transformation, where Q and P are dual, equality for P equals 2. Now, if you have equality at the endpoint of the interval P equals 2 and differentiate with respect to P, the derivative has a particular sign, and this yields an uncertainty principle for the quantum entropy. So the inequality, this Hausdorff-Young inequality, is maximized by biprojections, that is, projections whose Fourier transform are a multiple of a projection. And this plays the analog of the role of the classical Gaussian that maximizes the Hausdorff-Young inequality, as shown by Beckner and other people in 1975. Now, these relative entropy inequalities, because the cyclic and separating property shows that the algebra A and its commutant are related through the cyclic vector by what in quantum theory is called entanglement, and gives some quantitative measure of entanglement. And here is a diagram in our planar algebras of a relative inequality for quantum entropies. So, well, this is the relative Hausdorff-Young inequality, and differentiating it gives a relative inequality for entropies. The constant delta, small delta here, is just the square root of the Jones index. So you could do all sorts of things with these pictures now having reflections in different directions. And one object to study is a renormalization map. It seems that this converges, if you iterate this transformation B, to biprojections. And it could be something like a multi-dimensional central limit theorem, but this still has to be investigated. Many of these things are open problems. So the conclusion is that many things still need to be done, and some further understanding of reflection positivity, even in quantum field theory, would be extremely useful, connected with statistical physics, relations between those reflection positivities and other positivities, how to find new inequalities using the three-dimensional pictures in QAnon, and I think it's important to remember Samancic, Iraqi, and Faisal Gursey, who are not any of them remembered as much as some of the other people mentioned in these talks and at this meeting, but were very important in the development of this subject, because Vaughan you can find in all of it. So I'd like to end with a picture from the 30 years ago meeting. I wish I could be now in Istanbul. It looks from this picture as it might have been taken in Hollywood. And I wish you the very best of luck in the future. Thank you.
Arthur, please take it away. I had never seen the pictures you took during this 91 conference. I really need that you stop sharing the screen so that I can ask whether you have questions. Well, this was a really incredible talk. And do you have questions? I'm already getting ready to present a very close friend for the next talk, so it's getting more and more emotional. Marcelo, are you still there?
I must say that I spent a lot of time finding these pictures. They were not easy to find.
I mean, it's amazing. I mean, really. And for an opening talk and for Vaughan, I hope Wendy saw them all, and she did, I think. And I really thank you. Do we have questions? We also have a coffee break link, so you can catch maybe Arthur there if you want to talk in the hallways in this virtual world. Otherwise, we'll start in 23 minutes at 30.